Hello and welcome to my channel. John Smith here, and in this video we'll start to model a CPU for our emulated retro x86 machine. Before we begin implementing our new components functionality, let's think for a moment what actually a CPU is, what for it is used in the computer, and which parts of it we really need to emulate. A CPU is a standalone component which processes data. It performs arithmetic and logical operations on data by means of dedicated internal circuitry of the same name, ALU, while keeping the source and destination data in temporal internal storage, registers. Now, how does CPU know which data to process and what exactly to do with the data? Here's when reading and writing to address space comes, which could result in accessing RAM, ROM, or other devices which are mapped into address space. In cycle of operation, a CPU reads some address for a packet of specific format, which has some operation encoded into. This process is usually referred as instruction fetching. Instructions hold information on where to get the data from, what to do with it, and where to put the results. For example, Intel's 8086 CPU has about 100 instructions. And the good thing with x86 instruction set is that each generation of CPUs was backwards compatible. So if we start with modeling 8086 and encounter problems with some specific software or game requiring some instructions that we are missing, we simply can implement that instruction from superset of next generation CPUs like 186, 286, etc. So to create functional model of a CPU, we definitely need to emulate registers and instructions. Another thing to take into consideration is clocking and synchronization, but for now we'll skip these topics for simplicity and model a standalone component. As usual, first thing I'm gonna create a separate file for our new component. To get an idea of CPU registers, let's take a closer look at the manual. We see here that the CPU has a fixed number of registers. These are general purpose and can be used by the software in whichever way it wants, some of which are overlapping, which means modifying the contents of the lower part of the register, like AL, will modify a value of the extended register, like AX. And there are also some special registers, like flags. Different bits of this register are switched independently upon execution of different instructions, so we'll model it slightly differently for the purpose of usability. Now let's define some space where we will store our registers. And the registers themselves. As you can see, we respect register size by using corresponding data type in our code. And the reason we define registers as pointers is that this is a solution to make them overlapping. I'm gonna make a separate function to initialize registers. I'll map them into our register storage space in a way to create overlaps where required. Now for the flags register, we'll create separate structure that allows easy bit switching. For example, to set carry flag CF, we simply can write flags CF equals 1, instead of using shifting operations and counting bit number each time by ourselves. Now I'm gonna include our new component into the main source. And initialize it. So I think this is it for the first part. We've modeled all of the registers of our CPU. In the next video, we'll look into instruction fetching, instruction decoding, and organizing instruction execution. Do not forget to thumbs up or down to let me know if more episodes of this series should come or not. Hope to see you soon, and thanks for watching.